Okay, I'm going to introduce our speakers. Amit Bahl has been in the PCB industry for 20 plus years. He's the director of sales and marketing at CR Circuits. His passion is to empower tech companies to achieve their vision and change the world. Rockets going into space, self-driving cars taking up the streets, cancer fighting medical devices, protecting the country. He's ready to build any circuit board. Along with him is Atar Mittal. He's the director and general manager of the design and assembly division at CR Circuits. He's responsible for um, design and development strategies and process automation tools for complex printed circuits and assemblies. He's also currently engaged in the development of productivity tools for electronics designers that would have a tremendous impact on shortening development time. So Amit, take it away.
I think it's fantastic what you guys are doing, continuing with the educational focus. CR Circuits also has a huge educational focus. I would say that is equal to our passions of building circuit boards, is to working with designers on the challenges that they face and overcoming them. So we see ourselves as a partner more than anything else. Yes, we happen to build circuit boards and assemble circuit boards, but really we're a partner in crime. So again, thank you very much for this. And we wanted to talk about stack ups. I think stack ups is a very critical part of getting the right performance out of your circuit board. And so we wanted to talk about some challenges with selecting PCB materials, the process steps in manufacturing, as well as the impact on electrical performances. Okay, so table of contents. So I wanted to start off with the reasons for signal degradation, because if you don't have that in mind when you're routing your product and you're creating your stack up, then you're not going to end up with a board that functions properly. So we'll go through that real briefly, and then all the material properties, and then as well as the manufacturing challenges and some example stack ups at the end for HDI and whatnot. So here is Atar came up with this list of reasons for signal degradation, and we have materials on each one. At the end of the slide, we're pointing to some of those references. But we're going to focus in on point number 3, which is the signal degradation due to the copper and dielectric losses. So I'm talking about that today. Okay, so there's a variety of people in this meeting today. So I got to start here, but I know a lot of people are very sophisticated. So anyways, printed circuit boards, the materials, of course, they're made up of prepreg, copper foil, and then copper clad laminates or core materials, which is basically a combination of the prepreg and the copper foils. So, prepreg is basically B stage material, so it's going to melt during the lamination process. And then copper foils, there are a few types of copper foils and how they're created. There's electrodeposited copper foils, there's on top of the laminates, and there's also rolled and annealed copper, which is used in flex boards. And so basically you want to be clear about the materials you're using, because during the lamination process, the manufacturer has to worry about the final press out thicknesses. And so that's where all this comes into play. And as a designer, you should know where your prepregs and cores are in your design, especially when you're doing a controlled impedance or high-speed board. And a good manufacturer can predict the press out thicknesses very accurately. And also sometimes we run a first article to know ahead of time what exactly are the press out thicknesses if you have some interesting copper weights and some challenges there. So here are some of the basic material properties of dielectric materials. On the left, you have the TG, TD, and then on the right is some electrical properties. So I think everyone's familiar with what these are, but they're important to the manufacturing side when you're heading into complex design. And we'll get to that later. So TG and TD really have to do with the reliability of the PCB and how many thermal excursions you're going to have on that PCB. CTE is also a reason for some root cause failures. You have to be aware of all the CTEs in your system. And then from an electrical standpoint, you should know about your decay. And then of course, the loss factor of the material. So the dissipation factor is, I would say, one of the most important electrical material properties. So why do we care about materials is because, the signal degradation is basically a choice of, what copper and material types you select. So you need to pay, when you pay more money for a material which has a lower DK and a lower DF, your signals will be maintained. You'll have less loss. So, and for higher DK material, your threshold for the lying length decreases. So you have to be aware of, how long can my trace be with this DK value of this material? And there's definitely formulas to calculate your line lengths for that. And Atar knows those very well if you have questions about that. And just the point is to be aware of this. And then, different materials also have more consistent with their DK values at different frequencies. And then you have DF as well, which is directly proportional to the loss. So of PCB materials, electrical properties, play an important role in minimizing your losses. So when selecting your materials for your high-speed applications, be aware of the DK variation that can occur. Be aware of the glass bundles in your selection of materials because of the weave effect. And looking at hundreds of fab drawings every day, very few people specify the glass styles that they want to use in their materials. And that's kind of left up to the manufacturer, but I think the designers also should be aware, if they have a sensitive application or a high-speed application of these types of issues that can occur. So the glass style basically plays an important role in manufacturability as well. So if you have, an HDI board, you want to have more resin, because if the laser via goes through resin, it's a much cleaner looking via that's formed, and you can get good plating. And if you get good plating, then you have a higher reliable end product. And you can see the glass bundles and how they can get in the way in cross sections. So always request a cross section from your manufacturer. So the other part is that the copper you pick for your materials also plays a role in the signal loss because of the skin effect. So the lower profile copper is much better than from an electrical standpoint than the higher profile copper or copper with more T's. And the difference that you have to be aware of course, with low profile copper, you have to worry about the peel strength and what's the environment your board will be going into, because you still have to consider the reliability of the product. And then in terms of the decay, the lower the trace width or the thinner the trace width, the greater the signal loss due to the copper. So a lower decay value of the material allows for a thicker line, which basically, for your control impedance structures, and that would reduce your losses. So here's just a quick plot where you can see the direct correlation between signal loss and frequency. And then, the graph shows each material, or which materials I should say, could possibly perform better at higher speeds. I think materials naturally, bucket themselves. And so here's what we've kind of put into 4 buckets: normal speed, normal loss, medium speed, medium loss, high speed, low loss, and then very high speed and very low loss, which is RF and microwave. So just really quickly, so the normal speed materials are, the most common PCB materials like FR4s, and their decay versus frequency response is not very flat, and they have a high dielectric loss. So suitable for low frequency applications. An example is the Isola 370 HR material. Then medium speed materials have a flatter decay versus frequency response curve and have a dielectric loss about half of that of a normal speed materials. And these are suitable for, let's say, up to 3 gigahertz applications. Noco is a decent material for that. They've fixed their issues that they've had in the past with microfractures. And then for the high speed, low loss, you have your best, the flattest kind of curve, and it really reduces any unwanted electrical noise, suitable for very high speed applications. And, we like the Isola iSpeed. We also, Megtron 6s are very popular, and other materials in that regard. And then lastly, the last bucket of very high speed and low loss for RF microwave, let's say in the 50 or 60 gigahertz kind of a range, and Isola has a tachyon for that. So just another couple of slides, on materials and kind of where they fall into, and then, moving on to like a quick summary about, proper material selection and why it's important for your layout. So it affects, of course, the electrical performance of your signal traces. And so, material with similar decays as a point of best practice. I mean, when you want to make sure that your manufacturer, when they're doing your control impedance stack up, that they understand the prepregs that they're going to be using and the decays of each prepreg, and then roll that up to kind of a final decay. So that really matters and should be considered when the stack up is being created. You want to, when you're deciding your materials and your application, you want to match the CTE, or coefficient of thermal expansion, because I remember one example where in this application for aerospace, the customer filled all of their vias with a silver epoxy, and for whatever reason, there was a lot of heat absorption because of that, and that thermal expansion actually led to field failures. So, that's the worst scenario. You want to be aware of your CTE mismatches. And like we mentioned before, you want to opt for tighter weaves, so you get an even distribution of your decay, and then it's easier for your laser drills. You can avoid the weave effect, avoid FR4 for high-speed applications, and if appropriate, select low-profile copper. So any material that you pick, has an issue with manufacturing. We have to, as a manufacturer, you have to know what material you're selecting and how that impacts on the manufacturing floor. So our travelers basically change per material type. As an example, in lamination, you have different surface treatments for different materials, and you have to be aware of those. Definitely, there are different press cycles for different materials. So, nailing down, you want your fabricator to be used to that material so they know the temperature profile that needs to be used for that material and that stack up, and how many layers all impact the press cycle. And, we've seen lots of stack ups with, where it leaves us in a corner where the laminates used have actually different lamination cycles. So if that's the case, then you're really not going to, get a good end product. You're kind of painting yourself into a corner. So be aware if your manufacturer is recommending bond plies and what are the reliability issues with bond plies, whether that fits your application. And then, if you have a class 3 requirement, understand what that impact is on your design rules. So you can't have too small of a laser drill via, with, the class 3 design, because you need a certain amount of prepreg in between your layers for class 3. And so it'll be hard to meet your 0.75 to 1 aspect ratio on your laser drill blind vias. So understand how that plays a role into your design rules. So of course, on the floor, as the material goes through each department, we treat it differently. So especially in drilling, some materials you have to peck drill, some stack ups, with heavy copper, you want to peck drill so that you're not, smearing too bad. And then you want to make sure that, if you have mixed materials, that the manufacturer is using the right drill parameters that basically are the best, best between the two materials, I should say. So understand if you're causing the problem by selecting materials that are just really not compatible, or understand if, the manufacturer can come up with a good recipe for those drills. And then material movement. Before a manufacturer drills the board, they should definitely take a picture or an x-ray inside the board to see what kind of material movement has happened, and then optimize their drill for that. So there are, you have to have the right equipment, and then when you drill, you can use something called vision drilling, which is basically drilling off of a fiducial and taking the scaling into account. If the manufacturer doesn't have vision drill machines, then they're not going to be able to effectively drill tight or high dense required boards, and not get you the best annular rings. So again, going back to surface treatments for filling your vias with electroless copper. So the electroless copper is, if you don't have good electroless copper, then of course you're going to have a failure at that stage after you plate and all of that, and it'll come out through your cross sections. So you have to be super careful with that, that you know what the material properties are, and you know how to treat the materials to get good electroless copper. And I already mentioned the low profile coppers and the copper adhesions. So one question is from the chat is like, how do you minimize the movement of the material, or how do you at least know about the movement of the material? And all that comes through cross sections, and I don't think cross sections should be an added cost from your fabricator at this stage. We perform hundreds of cross sections every day for our customers, and it's really how and how we know that we're shipping a quality PCB that doesn't have quasi issues later on. And here's some of our preferred materials. For flex boards, we primarily actually solely use DuPont. For metal core boards, there are some options, and you can also kind of put your own aluminum in there and make your own aluminum based or aluminum backed, or have a center core for aluminum. So stack up design, like I mentioned, we're going to go into some quick examples. This is like the little bit of art and science, I think, in building a stack up, and don't be afraid to try different stack ups, but just talk to your manufacturer about it. They can definitely help you. So here's some things to really consider when you're designing your stack up. So in terms of like, first of all, whether your design is a single lamination stack up or it's a sequential lamination stack up, I think that is the first kind of decision you need to make. With HDI stack ups, you can get higher density designs. You can shrink your XY dimensions of your boards, maybe even your Z axis. You can shrink that, get a thinner board. So there's lots of advantages in size, shrinking the size for HDI, as well as some signal integrity advantages. And then, if it's regardless if it's HDI or if it's just a single lamination stack up, for your signal layers, how many are you going to need? What's your breakout strategy, et cetera? And then, don't mix your different signals on the inner layers. That should be avoided. We have a very detailed routing guidelines for best electrical performance. That's mentioned at the last slide of this presentation. And, and of course, I think you guys are aware that having two signals next to each other in your stack up will increase your crosstalk. So understand what your bit error rate would be, and understand that, is that okay or not? And then if your signal layer is not carrying any high frequency signals, then I guess it doesn't really matter in that scenario to have two signals next to each other. And then the number of ground and power planes. The purpose, of course, of a ground plane is to provide the return path to reduce noise and any sort of signal interference. So power planes are used to improve the decoupling, and it's shorter return paths, the better. So the number of the other parts is, for controlled impedance, we really want to think about where your structures are going to be, and where is the cores and prepregs in your stack up. Are you referencing a layer or plane through prepreg or through core? And then, if it's through prepreg, make sure the fabricators controlling the press out thickness of that. And then for sequential laminations, make sure that, one key aspect basically is, building from the outside in. So having two sublams versus, sequential lam. I always prefer the sequential lam process, but two sublams is very popular. The issue with two sublams is if the materials are different or the material of two sublams actually move differently, your final drill through the two sublams could be problematic. So if you have a final drill, you should put a lot of basically spacing to copper pour and all of that. I have a question about bit error rates. And so I'll pass that off to Atar when we get, towards the end of the presentation, so you can give an answer on how to calculate what is your bit error rate tolerance, I should say. So here's a quick example of a 10-layer board. It has 4 signal layers, 370 HR. So it's a signal plane, signal plane, 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 signal plane, signal. So 4, 5, and 6, 7 are cores with the power planes. You do not want to minimize the thickness of those cores. Having, let's say, heavy copper on a 3 mil core is problematic in manufacturing. And then also, just be aware, if you have a core that is signal on one side and plane on the other, and it's a thin dielectric like 3 mils, and the copper area isn't evenly distributed, you're going to have problems. The manufacturer is going to have problems in plating because really one side would require more plating of the copper and the other side less plating since it's a signal layer. So that becomes problematic, as well as the core itself can curl up in manufacturing, which can lead to crack traces and things like that. So, if you have a 10-layer board and you have 3 mil cores, I would say do signal on either side, make sure there's good even distribution of the copper, and take that into consideration in your design. Here's an example with 5 signal layers. Layer 1 references layer 2. Layer 3 is referencing layer 2 and 4. Layer 5 is referencing 4 and 6, etc. So if you look at these stack ups, we're showing the effective decay and what layers are plated, whether it's considered a signal or power, what's the copper percentage, and what's the final press out thickness. So these are some of the basics in the stack ups. So I kind of touched on this, but the HDI stack ups are very advantageous for reducing the size of your PCB and having a higher routing density. Considerations are, if you're going through 5 laminations in an HDI board, that the material should be able to withstand those thermal shocks. And keep your 0.75 to 1 aspect ratio in mind as well when you're designing your board and doing your stack up. Here's an example of the HDI stack up. I recommend only staggered vias for HDI stack ups because stacked vias are now known to be root cause failures. So you don't want to stack your vias. I think one of the questions for one of the attendees was, how many vias can we stack? And honestly, don't stack any of your vias. If you have a high rail application, you don't want to stack them. And there's some tests that you can do to prove out the reliability of your circuit board. And you can see that where you have your stacked vias, that would be a root cause for failure. And so one question was, what are the copper percentages? And so in this case, I only recommend the staggered vias. And if you look at this board, the layers 5 through 8 will be built first as a sub lamination. And then you would drill the via, let's say, and plate it like a through hole via. And you'll also go through a laser drill process. And so this laser drill doesn't require any extra lamination. You already get that from the first sublam 5 to 8. And then you will go from, you'll start building out from the center. So layer 4 layer 9 will gets laminated together. You'll laser drill down and you'll plate it. And if it's stacked, you have to fill and you have to planarize in most cases. So the planarization for any fine lines can become an issue. And planarization also can lead to uneven copper, which is all bad, let's say, for high-speed signals. So if you stagger, you don't have to planarize at all, for sure. And that's much better for manufacturability and signal performance as well. And so as you basically build out, so after 4 and 9 get processed, you would go back into lamination and laminate 3 and 10 and 2 and 11 and then 1 and 12 as well. And each time you go through lamination, you go through your plating process, your laser drill and your plating process. So from a time perspective, sequential laminations takes a long time. And we usually quote about 2 to 3 days per sequential lamination cycle. So if you have a 5 lamination cycle board, 15 days to build the product. And if at any time in those sequential steps something goes wrong, you might have to start from the beginning. So in single lam processes, you build all the inner cores in parallel and you laminate at once. So single lam boards are much quicker to build versus a sequential lam. But of course, there's a difference in the performance, and there's a difference in how many layers you might need, and the size of the board, and the thickness of the board, and all those should be considered when you're designing your product. So there's a question of, on sequential process, do we use a button plate for those plated layers? Yeah, we use a panel plate for sequential lam. So, and then here's another example, which kind of shows a lot of signal layers and where you can have all your impedances. And when you have a stack up that you want to do, that you think where you would want to put your impedance structures, you can talk to us and we'll kind of help you out with that. And like, where should your impedance structures go? What layers they should be referencing and things like that. So there are a few questions on, like, when you do staggered vias, is there a preferred pad to edge or pad to edge dimension? How much staggering, etc. Pad to pad spacing is just like regular spacing. So I should say 3 mils from pad to pad. But, when you're staggering, you can cheat a little bit, basically. And that I would say talk to your manufacturer. It really depends on the material movement. You can't take one design rule and apply it to different materials and apply it to different stack ups. You should really talk to the manufacturer and make sure that that design rule is going to be effective for that stack up. And I know it's a pain to talk to the manufacturer sometimes, but that's why manufacturers really are your partners, because that's how you get the most effective performance of your board and the least cost. Because as you go through the lamination cycles and something is designed kind of on the edge of capability, a fabricator won't tell you that at the time of manufacturing. But if you talk to them earlier on, they'll tell you all the rules that are best applied, because you still have the opportunity to fix those or design it for manufacturability in the first place. If you wait till the end and submit a design, and the fabricator is not going to start telling you every single edge case, because we would never build your board, and you might get spooked, go to another fabricator. Like, there's so many things that can happen at that stage. So the reason for this discussion is to understand that stack up design is very much a manufacturer's in the manufacturer's ballpark, and as well as considering the electrical performances. Some manufacturers don't think about the electrical performances, which is not leaving it all up to the designer on that side. But if you have a good fabricator, they would understand the electrical impacts of the stack up decisions are having on your design as well. And I think that's a key point. And before I was talking about two sublams and the material can move. So material movement, just to clarify on that point, is that when you laminate and you have prepreg, which is, I guess melted, your cores can shift around during that lamination cycle. And so at the end of the lamination cycle, you want to measure how much has each core shifted in that lamination process, because you have to rescale your drills for the best center of all the layers of those cores as they have shifted. So that's one example of material movements. And then there's just scaling, XY movement of the material itself as it goes through manufacturing. Some manufacturers use a very rough scrubs to prep surfaces, and the rough scrubs will actually move the material, especially if it's a thin core, will stretch the materials. So you want to use a non-aggressive clean on those and those thin cores. And so your manufacturer should know and have all their kind of recipes dialed in for that. So this slide is really, what's in the PCB designer's domain to minimize the signal reflections and get a good performing product. So what's key to me is like third bullet point is, run your impedance traces, kind of on internal layers. I think that's just the best way to do it. And make sure you have solid planes, reference planes, to minimize any sort of noise. And again, we have a design guide, with all the routing guidelines for that. This is a slide which has all the kind of references. And if Atar can chime in, I wanted to answer that one question about kind of knowing what your budget is for signal loss. I think you're better qualified to answer that question.
What is the question?
So the question is exact, because I kind of mentioned very generally, to consider, what is your budget basically, and so how do you calculate or know, what is your budget?
Generally, if depending upon the communication interface or the the type of signals which are the high-speed signals, or what interface protocol is basically going on those signals, there is in the standards are given some of the guidelines for signal distortion or noise margins and all those kind of things. So based on that, roughly the sum of the budget is to be allocated for manufacturing tolerances. Some of the budgets have to be allocated for for the noise margins and signal distortion, etc. Roughly, whatever is the let us say the length of the line also, because most of the losses in the signals occur, they are proportional to the length. So if the line is long, then basically your overall signal loss will be much more. So therefore, you have to reduce the length of the line if you're finding that actually the budget is going above. So those are some of the techniques that one will use, but it is good idea to first of all get an idea of what is the highest signal frequency content in your high-speed signals. Most of the time, you will not get an idea of straight away of that. You will get an idea of, let us say, what is the fastest rise time of the signals, or what is the maximum data transfer rate. So we have certain references here which can translate, given any of those three things, either the highest signal frequency content, or the fastest rise time of a signal, or the highest data rate transfer, which is going on those signals. You can always calculate a the highest frequency content from there. From the highest frequency content, you can define, you can actually, there is a critical length, and that if the trace is longer than this, then it has to be treated as a, is prone to signal integrity problems, and therefore it has to be treated as a control impedance line, and we have to be ensure that the reflections are controlled, and we have to ensure that actually the signal attenuation does not take place when the signal goes from the receiver to the from the transmitter to the receiver. It does not get attenuated so much as to produce errors in reception. So those kind of guidelines, some of those calculations, how to calculate loss, etc. We have certain design guides and certain blogs, articles, which basically give that. Of course, there is plenty of literature available. Books are there, but generally we try to condense all that information into some kind of a blog article or a design guide. So that is the thing. There is a question here. Which board material type would you recommend for boards with PCIe 4.1 differential pair routings? I would say that iSpeed would be a good material. Megatron will be a good material for that one. How would I, what is the next question? How would, Amit, that the next question, I think you can answer.
Yeah, I looked at some of the questions. There was one about whether we can do a virtual tour of our factory, and the answer is yes. I know it's weird times with the COVID, but we're still getting audited once in a while, as well as we can do virtual tours. So if you want to see a fabrication and the equipment and kind of walk through what each piece of equipment is used for, and understand the flow of manufacturing, we can do a walkthrough of our factory. Also, we can do a walkthrough of our assembly line as well, if you're interested in that. And we will be sending out the slides, of course. I think that does it for the technical questions.
There's a question here, I think by Gilbert again. Copper wrap plating required for through-hole vias.
Oh, I see.
You have any thoughts on that?
Yeah, copper wrap's super important. It's required by IPC to do a wrap. So it's not necessarily optional. I think the question is like, is it an optional thing or not? It's not. Yeah, cross section will show that you have enough copper wrap. So that's why you get your cross section from your fabricator. Did I answer the question?
The copper wrap is generally, as far as I understand, is required when you have to fill the via and you have to plate it and and plate shut and planarize and all that.
Copper wrap, yeah, copper wrap when you do a filled via becomes more challenging. That's all.
Right.
But the copper wrap always has to be there, and then after a filled via, the cross section should show that there's still enough copper wrap.
So maybe the answer should be that when you have a through-hole via and you are filling it, then there is definitely a very well-defined copper wrap requirement as per IPC standards.
Yeah, for sure.
And it definitely varies from class 2 and class 3 boards.
Class 3, they just waived to class 2 requirements.
Okay, I see.
So
okay, but general through-hole vias, it is not that let us say strict, because in general through-hole vias, you will whatever the plating you are doing in the via, and there is a a reasonably good amount of, annular ring, then basically uh, the the general plating will take care of that. That's what my understanding is. Amit, you can correct me if I am wrong.
No, you're right. That's correct.
Okay, now bit error rate. Now bit error rate. This is Mr. Cherry Litson's question. Bit error rate is basically when you are transferring, data transfers are taking place. Bit error rate generally is given in terms of, how many bits per million bits of information that has gone there. When you know the bits are being transferred sequentially over a, a serial line or differential pair, and so basically that is the definition of the bit error rate. How many bits are erroneously received at the receiver, which means if it was 1, it may have been received at 0, and if it was 0, it has been received as 1, etc. Not sure how this scale of measurement works. So, so, so bit error rate is basically uh, gets affected by the eye diagram of the channel skew and jitter and all those things affect it. Slightly a detailed topic, cannot be covered at this stage here, but I think the definition is roughly what I said, that number of bits received in error over a million bits or something like that. Yeah. Okay, what are the other open questions I can see? Oh, I see. Okay, so let us see. Let us go down below. On the stack up, please elaborate on copper percentage. Now, let's put it this way. There are, as indicated over there, we have the various layers, various conducting layers. You can have a plane and you can have a signal layer. So generally on signal layers, more of the copper is ashed out. So the remaining copper percentage is roughly of the order of, 20-25%. We have, the stack ups which we showed, the copper percentage on signal layers was shown as 24%. That's an average thing. Every manufacturer has different kind of things, but from our best, uh, let us say, practices, we have found that actually 24%. If we use 24% as the copper percentage at the design stage, then actually it is quite okay. Then the manufacturing comes out pretty fine. On a plane, we have used 64% as the copper percentage in those stack ups. Now, generally, planes will have a copper percentage of more than that. But when you put the percentages, what we have indicated over there are, when you do the manufacturing on one big panel, you will put 4, 5, 6, 10 boards or something like that, and there will be spaces in between them and all that, and there may not be any copper in there. So that way the copper percentage overall in case of a plane will get reduced, and that's the reason why we use 64% over there. So generally, if you just look at the design itself, then maybe the copper percentage on a plane may be as high as about 80%. Okay, how much micro versus via stagger is preferred? I think that question was answered. On sequential lamp construction, do you button? Okay, that is also answered. When staggering on micro via, how much is stagger? Is there a, yeah, tangent? I think there are a lot of questions on staggering here.
Yeah.
And Amit, did you take care of all of them?
I'm going to send kind of a design rule guidelines for staggering.
Okay, I think that's an important thing because, the spacing between, how much of overlap in staggering is there and where the overlap should occur. That is very critical. Yeah.
And of course, laser drills are extremely accurate. Imaging with LDI is extremely accurate. So, you can do, very accurate things with laser drill. But anyways, I'll send kind of like the generic design rules.
A material movement. You want to say something on that? What is material movement?
Oh, I think I answered that one.
Oh, really? Okay. The trace affects my electronic bit error rate. Yes, if the attenuation is too much, if the material is very lossy compared to what you're trying to achieve, and let's say take a differential pair LVDS kind of signal, then definitely if you're running a very long trace and all that, it is quite possible that the bit rate at the receiver will be uh, more than what is permitted in the standard. Yeah, the way the term was used, I wasn't sure how this was being. Okay, will do. Okay, all right. Is there any other open question?
I think we're good. I'm gonna stop
Yeah,
sharing my
yeah,
screen.
yeah. Okay, all right. I'll mute myself.
Thanks, Atar. Thank you very much.